energy physics, escalator physics, design, construction, and operation. Professor Misra has made significant contribution in the research, design, and development of the state-of-art technology of the particle physics experiment, proton, antiproton, synchrotron, electron, positron, LINAC, and proton superconducting LINAC. Professor Misra has significantly cited fundamental physics and discoveries paper including the discovery of top quark, B quark, meson production, nuclear shadowing effect of J pies, dimuon production, and discovery of hypernuclei and associated eta meson production in pion-nucleon collision. And lastly, I would say he is the class fellow of Professor Anjana Jha, HOD Physics Department, Nsut. I welcome you, sir, in this plenary lab. Thank you very much, sir. You can start.
Thank you for your kind welcome, and thank you, Ranjana, for sending me the invitation. And I will try my best to address the subject of material science. I guess you can see my slide, the first slide, which is my Fermilab laboratory building, where most of the scientists and administrative staff have their offices. This building has been my home for the last 33 years, so it has been very long. When Ranjana sent me the message about this conference, first I thought, what can I talk about material science? And then after a few hours of thinking, I said, oh, there are a lot of material science we do. It just depends on how I think about it. So I will give you a brief overview of what is happening here, what's going on with in the material science, and leave you enough time to ask me any question you have. Another reason of showing this picture to you is, I guess you can see my mouse. The India's tricolor has a permanent post in front of my laboratory. Every morning the flag goes up at sunrise and goes down at sunset. And we are very proud to see our flag going up on this flag post. And it has been there for the last 24 years on its permanent post. So let's see if I can move my slide. No. Okay. So here are my thoughts in preparing this presentation for Indian colleagues. So the way, at least I think about it, and I've been involved with Indian science now very heavily for the last 20 plus years. That the solution, there are a lot of challenges we face in India, and the solution to most of the challenges that I can think of has roots, the solution of that has a root in physics. So I've been working on three major challenges that, from my perspective, India has in front of it for its growing economy. That is energy, environment, and health. And all of you know very well that the world is facing a huge environmental problem. This global warming is affecting all of us. And there is an intergovernmental panel on climate change. India is a member of it. And its reports and calculations suggest that nuclear energy has to play a significant role in this energy model if we to reduce the global warming temperature by 1.5 degrees. Okay. And no matter which country you put in or take out of this global model, almost all paths requires India to be a major player in solving this environmental problem of the world. And And from my perspective, India is in position to lead, and India should lead the world in solving our own challenges and helping the world for generations to come. So, so now I will move on to what is happening at my own laboratory. So this is an aerial view of Fermi National Accelerator Laboratory, which is about 35 miles west of Chicago. This is the building I showed you the picture of. This land, all of this land you see in this picture is the Fermi Lab. It's about 100,000 acres. This big circle you see here is the famous Tevatron. This is the proton and antiproton collider we used to run at 1 TeV each in the proton and antiproton energy. At present, it has been decommissioned in a dozen months. So our accelerator chain is proton starts from here. It goes into this booster accelerator here that takes it to 8.9 GeV. From there, it is transferred into this kind of octagonal elliptical ring, which is called main injector, and there is another ring inside it. It is a recycler ring that takes the beam to 120 GeV, and that's the send out in this direction to produce muon beam and neutrino beam. This is the machine which I helped design and build and run for roughly a decade at Fermilab, and I will show you the pictures of this thing. So this is where my life started at Fermilab, and this machine itself has a lot of material science in it. There's construction design. And at present, we are building another machine, which is right here in collaboration with India, and that will essentially double the beam power of Fermilab. And I will tell you why India is interested in it and why India is collaborating on it. So what's the physics program of Fermilab? We have a wide range of physics program. We have roughly about 500 physicists on the staff and about 1,000 to 2,000 physicists, depending on the month, stationed at Fermilab or in our collaboration, working on different experiments. So the way we think about physics and high-energy physics is different frontiers. So Fermilab leads the world in intensity frontier physics. We have a high-intensity proton beam, which is roughly 2 megawatt of beam that we want to produce. At present, we can do about 1 megawatt, and we have a proton improvement plan, lack of any better name, that we are working on. We have a very broad neutrino physics program at Fermilab. India is collaborator on all of these experiments. We have deep underground neutrino experiment, which is a long baseline experiment. Beam leaves Fermilab, and through the Earth it travels all the way to South Dakota, which is 1,300 kilometers away. All of you are physicists, so you know that neutrino travels almost without interacting, or a few interactions from here all the way to South Dakota. And we are building a 40 kiloton liquid argon detector, which I will show you a picture of shortly at that location. We also have a short baseline neutrino detector, which is roughly the same technology of liquid argon. We are working on rare decays, muon to electron conversion, or measuring the precision measurement of muon G-2. So these are Fermilab-based experiments. We participate in an energy frontier experiment at LHC. I saw on the schedule, on the agenda that Archana gave a talk yesterday about LHC experiments. So you must have learned a lot from her about the world participation in LHC experiment. We also work in astrophysics, where we have telescope, we participate in construction and operation of telescope around the world. Our main collaboration is in Chile and in Argentina and also on South Pole. And to do all of these physics, we spend most of our time doing R&D in development of these detectors, which includes quite a bit of material science, and I will try to give you a few examples of it to get you interested in some material science involvement for the programs here at Fermilab or programs in India that we are developing. So this is Fermilab's main accelerator picture, which is operating right now. This is called main injector. So on the bottom here are electromagnets. The blue ones are bending dipoles, and the red one is focusing quadrupole, and it alternates between focusing and defocusing to focus the beam in both planes. So if it is focusing in X plane here, it defocuses in Y, and here it reverses. So we get almost a circular beam through this machine. This machine is 3.3 kilometers in circumference. There are roughly about 600 magnets. I'm very proud of this machine because every one of these magnets had my hand on it. On top here, you see is another machine, which is called recycler ring. And this is a material science challenge. This magnet and the dipole here, and this dipole here, you can see there is a difference. But this one, or you can barely see, this one does not use any electricity. This one is made up of a permanent magnet that you have it on the refrigerator to hold the newspaper or photos or whatever you want to put it. This is the same material we use to build a 3.3 kilometer machine. Since then, we have been participating in this material development, and now actually we can build this machine, which will be roughly about 1/3 in circumference. So the material of making this permanent magnet has improved quite a bit in the last 20 years. But we cannot change this machine, but that just to tell you that the new machines that we are building, including one in India, are using the new magnet technology or new permanent magnet to build this accelerator. This just to show you that the accelerator does operate. This is in the blue here is the intensive number of protons delivered to the target for neutrino production. This is for last fiscal year of the United States, which starts in October and ends in October. And you can this is what we promised the Department of Energy that we will deliver. We are hoping that we can deliver, and we are roughly somewhere in between. So our machine operates very efficiently, and this intensity here is roughly 2 times higher than when we designed this machine about 25 years ago. So, and still we have not found a limitation of this machine. So this machine will be used for our future neutrino experiment. And this is the schematic of our neutrino program. So this is the same building again. The proton from this accelerator, which will sit about here, will go up the hill to a neutrino production target, which is part of the main injector that I showed you. Then the beam goes through Earth. It will travel 1,300 kilometers, and it is going to have a detector of 40 kiloton at this location in a gold mine, roughly about 1 mile underground. India has a program called Indian Neutrino Observatory. It was supposed to be built in South India due to some environmental issues. I believe it is being moved to North India, but the final location and final design placement has not taken place yet. So why are we sending this beam of why are we producing 2 megawatt of beam and sending it all the way to South Dakota? There are a lot of mysteries of the universe, and that's what the physicists we are trying to solve. So this is roughly the physics goal of this deep underground neutrino experiment that Fermilab is fully focused on. So as you know, there are three types of neutrino: electron, muon, and tau, and they are antiparticles. So we are trying to study how their behavior is different, because you know this whole universe is made up of matter, and we don't know what happened to antimatter. And maybe we believe that neutrino holds the answer to what happened to the matter. Okay. So we send when the neutrino comes from sun, we don't know exact origin of it, what flavor it started with, but in accelerator we can control the flavor of neutrino. We can produce muon neutrino, we can produce anti-muon neutrino, and we can see how many electron neutrino we see there at our detector, or how many tau neutrino we see. We know that everything which left Fermilab is a muon neutrino. So if we see electron neutrino and measure it with high precision, we can tell how much it oscillates. And then we can send anti-muon neutrino and measure it again and see if there is any difference between muon neutrino and anti-muon neutrino, say, for example. So this will give us a lot of clues about antimatter and why this is a matter universe, not an antimatter universe, and what happened to antimatter. We are also building our detector with the mind to look at supernova. Hopefully we'll be lucky to see an exploding star. And that means we can see the complete formation of black hole through measuring neutrinos and study the depth and formation of these objects in the universe. The size of this detector is very large, as you'll see in the picture next. So we have a lot of protons in this detector. And so the detector is designed to look for proton decay, a signal which is supposed to be very rare, but it's predicted by theory. And maybe if we see some decay, proton decay, at least Einstein's unified theory of matter and energy can be addressed. So it's a very intense physics goal on one experiment, which is supposed to take data sometime later this decade. First with cosmic rays, and then with beam from Fermilab Accelerator Complex. So this is the 1/4 module of the detector. This is a picture, a schematic of it. It's 66 meters long, so roughly the size of a soccer field, and about 20 meters wide, and about I will say about 20 meters or so tall. So not 20, but 10 plus meters tall, 12, 13 meters tall. And this is full of liquid argon. This one holds about 6 kiloton of liquid argon, and it is full with electronics on the top. So liquid argon is at minus 180 degrees centigrade, and so at present I'm personally working on an R&D of electronics to operate very efficiently with low noise in liquid argon environment. Okay. So again, you can imagine that this has electronics material going into liquid argon, which has to sustain its life for 20 years without corroding or anything inside the volume, keep the liquid argon pure. So all of these things boils down to doing material science, and its focus is to make an environment which is green, efficient, and noise-free. So this is one of the programs that our colleagues from India is also participating. On the accelerator front, so this is again the Fermilab accelerator complex. We are building this new accelerator where I will tell you about material science and India's program. This is a 800 MeV superconducting LINAC that is under construction right now, which will produce a 2 megawatt beam. So what has been constructed so far is this PIP2 injector, which is here has a copper RF tube. And just to give you an idea of, this is an ultra pure oxygen-free copper with a surface precision of a micron. And it's supposed to accelerate beam to 3 MeV, 3 million electron volts, in about a meter or so, about 2 meters in length. So when this thing is built and what do you call it, prepared for operation, this is a very clean process to deal with. So for the inside of it, these are very high power RF coming into this RF tube. The next year is a superconducting module, which has been partially fabricated in India, right in New Delhi, at IUAC, Inter-University Accelerator Center, which is near JNU. I guess some colleague from there is also participating in this workshop. This is where I will focus our material science work on. Okay. But there is just a lot of other things going on in building this module, and you can see that India is an integral part of this collaboration. So now you will ask, okay, we're doing physics in Fermilab. Why are you getting so interested in India's program? So one day I was flying back from Mumbai, visiting my family. So one of my physicists colleagues handed me this book. It's written by J. Venkat Raman on the life of Homi Bhabha. And I'm pretty sure all of you know about India's nuclear program and India's ambition to be a leader in nuclear energy. And Bhabha introduced this program in 1950s. After that, the Bhabha Atomic Research Center was built in Mumbai. But his thought was not only to build a nuclear bomb, but he was also interested in developing Indian capability on all the basic science and make India kind of not depend on West for this development of self-sufficient in energy and technology. So this is a very inspiring book. If you haven't read it, you should read it. It's not that thick, it's only about a couple of 100 pages. So it gave me an idea about some India's need and where we could help. So India's nuclear program is essentially focused on three-stage nuclear program. When there used to be Planning Commission of India, its name has changed, but it's works roughly the same way. Any program of that part of the government always comes with three stages of nuclear program. India is spending a lot of money on it. The pressurized heavy water reactor, I don't know whether there is one nearby New Delhi, but there is many under construction in Rajasthan. In South India, there is one in Tarapur. So many of them are operational or to be operational in India. India is building a fast breeder reactor. There was a prototype built at Kalpakkam at Indira Gandhi National Institute of Research, which is also known as ICAR. It essentially takes the plutonium from this reactor and puts it in the second stage reactor, adds thorium to it for energy production. After the first prototype, a 500 megawatt reactor is also under construction. But the key word in this thing is thorium utilization. India right now depends on the West for supply of uranium. To get India out of the need for importing uranium, India has a vast reserve of thorium, and thorium is not a fissile material, but if you put in a neutron on it, induced from a proton beam, it will become a fissile material. And that is the accelerator-based induced nuclear production. The third stage plan of India is to put in the processed fuel from here into the reactor and add thorium. But what has been under discussion and now is under construction and at a project called Berha in Belgium is the accelerator-based nuclear energy production. So this is a schematic of the technology that we are working with. Here is the SRF proton LINAC. It's the same LINAC that I told you about, which is under construction at Fermilab in collaboration with India and many other countries. If it produces 1 megawatt of proton beam, it goes through a reactor chain and it will produce roughly about 50 megawatt per megawatt of proton beam through this cycle. To run this accelerator, we will, because we have not been able to make this accelerator very efficient, the efficiency could be 10% to 5%, based on how well we do our material and accelerator technology. So it can put for every megawatt of beam, we could put 40 to 30 megawatt of electricity back onto the grid. So it will become an energy production machine which utilizes thorium, because you put in a neutron on thorium, it becomes uranium-232, I believe, and that is fissile. So this is a technology development that is going on at 3 institutions in India under Department of Atomic Energy, and this is where I intensively have been working for 2 decades, and then I'm now focusing on some new R&D because construction is not my expertise. So in about 10 years working through bureaucracy, we have 2 agreements that I just want to show you the first pages of it, and you can look it up, the reference I've given you. It's an implementing agreement between the 2 countries for area of accelerator and particle detector research and development for discovery science. From the US perspective, it is discovery science. From Indian perspective, it is working on technology, which is needed for India's program. Before this, there was an agreement on science and technology. And if anybody tells you that there are issues with intellectual property, you should read this document very carefully. For scientific collaboration, there are no such issues. It's very clearly written, and every word of this document is written by me and approved by the higher ups in the government. And it is signed by the two governments, including the Prime Minister of India. So it's a very high level document. After that, we wrote this Project NX1 for a very focused collaboration between the two countries, what the two countries will do, which was also signed when Prime Minister Modi visited United States in 2014. So this is another thing that we work to share technology with India for India's program. So now let's focus on material science. So material science, because if you want to build this accelerator, this accelerator, as you can see by this cycle, has to be very efficient to put power on the grid. So everything in this accelerator starts with material science. So this cavity here is built out of pure niobium. The triple R of this niobium is 300 or better. And at present, niobium is the only material we can use to make this superconducting cavity. We have tried polishing copper, polishing other material with niobium to make it superconducting. Nothing works. Nothing works with the efficiency we like to have. So any new material, there are a lot of studies going on room temperature superconductor or liquid nitrogen temperature superconductor. And if those technologies can be pushed, one can make these cavities cheaper, better for the operation of those accelerators efficiently. As you also know that India is not a producer of niobium. It essentially imported from either the United States or Brazil. In building this cavity, there are a lot of techniques. So first you have to weld it, and this is not welding in your weld shop. Welding is done by electron beam, and the direction and circulation of the electron beam is a state of art itself. Because when you're handling beam at this location, electron beam welding at this location, as you will see in the next picture, it's quite a bit of challenge itself. The surface of this thing must be ultra clean. We handle this whole thing in fast and clean room. It goes through a surface treatment of chemical and electropolishing to make the surface as smooth as possible. It goes through a cookery of heat treatment, which is also changing the material characteristic of niobium a little bit, and I'll show you a picture of it. So this, starting from niobium all the way to cavity, it goes through more than 2 decades of material science development that we at Fermilab and our colleagues at many national and international laboratories have worked on. So one of the material challenges is to come up with a new superconducting material which can have similar mechanical properties for building these cavities. So these cavities, we like to make it cheaper, we like to make it better, we like to make it simpler, but we like to have its best quality also. And so what's plotted here is the accelerating gradient of the cavity and its quality factor. Accelerating gradient, larger the accelerating gradient, shorter the machine, better the quality factor, less cryogenic it will need. So, and two are fighting with each other. As you can see, higher the gradient, less quality factor. And we always work to make this thing as high as possible. This is a picture of inside of the cavity. This is where the electron beam went to weld the cavity. And you can see a small spot here, which was made this cavity quench at this location. And we could not repair it by a lot of treatment of this surface. So you get, as you will see in the next picture, so this is a microscope picture of that pit on the cavity. This is where the electron beam welding happened. You can barely see a pit here under a microscope. When you expand that picture even more, this is one grain of niobium. You can see one grain started here and here. And in between, there is this defect. This is the 3D microscope picture of it. This is what was causing the quench of the cavity. So we went with a laser to fix the pit. But you know, the time and money it takes to go through this R&D to fix one cavity is very large. So and one cavity roughly costs about $250,000 in making. So we like to make it cheaper, but at the same time, we cannot afford to have all these pits and repair. So idea is to make this surface not have these kind of material problem. So this is one area where we have improved quite a bit. We don't generate the pit anymore, and our surfaces are relatively doesn't have problem with the grain boundaries to the best of our knowledge. So I already described to you this picture, the high energy accelerator. We like to have higher gradient, we like to have higher quality factor. And these are different machines which are either running in the world or being designed in the world. And these are their performance of their cavities. So one day we were doing materials research at Fermilab, processing these cavities. So this is the performance of one cavity. And during the heat treatment, scientists introduced some nitrogen, some hydrogen, and other gases to see what happens to the surface. And by introducing nitrogen under heat to the cavity, we increase the quality factor of this cavity by almost factor of 3. So this has become a new area of material research that we are doing, because actually we don't fully understand what happened, what changed the characteristic of the niobium surface that made this quality factor go up. Although now we process off all of our cavity with nitrogen treatment. But physics, I don't think we fully understand what happened. Another area of material research where we are focused on has to do with, again, if you look at Indian program and Fermilab program or program at CERN or in Belgium, we deal with very high intensity or high radiation environment. And inside the nuclear reactor, the radiation is much higher than anything we deal with our accelerator. But what happens in our accelerator, this is a beryllium window, and proton goes through this window. And you can see that on the grain boundaries, it develops cracks. Okay. And once it develops cracks, after a while, it will crack and vacuum fail. So we are doing quite a bit of work to improve the strength of this target or with this window. Other thing, you can imagine that 2 megawatt of beam is being bombarded on a carbon target, and pions are produced, and subsequently muon and neutrinos are produced. 2 megawatt of beam on a target makes the target very fragile, very similar to what happens inside the nuclear reactor. So there are a lot of research going on in optimizing materials so that it can survive a high radiation environment and doesn't become fragile. Okay? And some of the material that we are trying to develop is to enhance the thermal shock properties of radiation damage resistance. And what we are trying to develop is what my colleagues calls it high entropy alloys or nanofibers to see whether we can make better target or better radiation hard materials. So this is how much I wanted to say about radiation program or material science program. Other thing which as India's need and for that matter world's need, that we use our accelerator technology to give it to industry for doing a lot of environmental work. As you know, water system in India is very dirty. United States used to be in that situation in the late 60s. Our lake, the Lake Michigan, used to be very dirty, which is only 30 miles from my home. You could not take a bath inside Lake Tahoe. And now you can see water for meters very clearly. So United States has put in a very concentrated effort in water and waste management treatment. And one of the technology that is being used in developing countries like South Korea, for example, has to do with using beam. And here is a list of all the environmental application of beam, and each and every one of them has applications in India. If we want to clean the environment, the river, and the fossil fuel, which have been dumped everywhere around the country. But I'm not an expert in this thing, so I will not go into detail of it. But I know the technology is there, and this is available for collaboration to anybody who wants to collaborate. Other area which is very dear to my heart has to do with health application that we have been working on. Myself, along with many of my colleagues, are great advocate of proton radiation therapy. Fermilab built the first machine of proton therapy at Loma Linda University in California. Since then, at least 2 or 3 dozen machines have been built around the world. India does not have a single machine. India mostly uses X-ray or electron beam for radiation therapy. So here is the difference. This is the standard therapy is say for the brain tumor. The beam is given to the patient, and the beam, a large amount of beam has to be given because it's electron or photon, and the beam travels through the patient's brain in this case, and damages the tissue before and after. In the case of proton machine, you can tune the beam to exactly hit the tumor with a precision of a micron, and no radiation goes downstream. So this is a technology that we have been working, actually telling my colleagues in India to develop, and hopefully somebody will like to get involved. It's a help to humanity in India or around the world, and it's India's economic situation right now is there to build a few of these machines. There is another application is in radioisotope production for injecting dye into human body for making therapies or diagnostic. Variable Energy Cyclotron Center in Calcutta is building one facility like that. So, in summary, I told you that Fermi Lab is a premier research laboratory in high energy physics. I welcome if you are in the United States, you can come and visit us. It's one of the few laboratories which are open. You can come here with a few days' notice, or at least a few weeks' notice, and visit us. We are focused on fundamental research, but to do that fundamental research, we do a lot of material science research. We are working with India on at least energy and its application of accelerator technology to environment and health. And I firmly believe that economic and scientific economic condition in India and the scientific and technical manpower in India are not issues anymore in the 21st century. And India could focus to implement this technology for its need. And that's where I will end. I will welcome your question or comments. I see some questions, but I will let the chairman decide.
Yes, sir. So please, you can address the question.
Okay, what techniques have been used to control background radiation or low energy radiation in detection measurement? So radiation is a very serious issue. We work very hard on our beam to not leave our accelerator. A huge amount of work goes into focusing the beam so that focusing and controlling the beam, we have, say for the main injector, we have about 400 radiation detectors. And if any one of them sees a small amount of radiation, we stop the beam and fix the problem. So it's an interactive procedure. We have, I guess you are talking about how do we control the radiation leaking from an accelerator. So we have precision magnets to control, and we have very fancy control system to fix the radiation problem.
Okay, so any other participant, please, you can raise your hand and then we can unmute you directly. If anyone from the online participants has any question, then please let me know, raise your hand. From the offline audience, if anyone has any question, then please come on the podium and ask your question. Anyone? It's the best time to interact with Professor.
I see a few cameras coming on, but I don't know that those persons are unmuted.
So, okay, then if no question,
Okay.
yeah,
Good.
I would like to invite sir to thank.
So thank you very much, Professor Misra, for sparing your time, and especially in the odd hours, because you know that there may be around 12:30 night in the USA. So we are very much thankful for sharing your valuable knowledge with us, and the whole committee of ICAMET 2023 heartily thanks you for your time and being with us through this virtual mode. So thank you so much.
Thank you for asking me to give a talk. And one thing I want to say, if anybody wants to collaborate, you can talk to my colleagues in India, at Delhi University or IUAC, and there is a venue to have your graduate students and professors work with us. So with that, I will sign off. It's 11:30 p.m. my time. And thank you, Ranjana, for asking us to give a talk.
Thank you so much, sir.
Okay.
So now,
Bye.
yes, please. Sir. So any other question, please, you may ask. Professor Misra is still with us. So you have any query, any clarification or something you want to add in your knowledge, so you please can ask. You may also write in the chat or raise the hand through the Zoom, and then we can unmute you and you may ask the questions if anyone want. So if not, then we proceed ahead. So next is the presentation by the company presentation, and so you know that we have the sponsor of MTech Gatan. This company is sponsoring this conference. जुड़े हैं ना अभी तक companies.
Hello, sir.
Good morning, sir. Good morning. So welcome
Good morning,
you in this conference, and very much thanks again to you because you are our valuable sponsor of this conference. So we are very much thankful, and I tell you to the audience that this session is for the company presentation of MTech Gatan. He will tell in details about their products and what you can do in the material science with that help. So I heartily welcome you in this session and request you to kindly proceed for your presentation.
Okay. Thank you very much, sir, for giving opportunity to present about our cameras.
Sir, I just let me interrupt you that I would request to all the participants or the coming speakers of all the sessions, please give your presentations so that we can load them timely and the sessions could be run uninterruptedly. So offline speakers especially, please submit your presentations to the respective rooms according to the schedule. Thank you. Yes, sir, please proceed.
Yeah, can I see my screen, sir? Is it okay?
This is perfectly visible, sir.
Okay, sir. Okay, sir. Thank you for very much for the organizers, to the organizers for giving us the opportunity to present about our product, basically. Basically, we are the Gatan ICAMET basically manufactures products that related to electron microscopy. So that comes from like cameras for imaging in TEM and analytical products of like EELs, and then we have a cathode-luminescence systems on SEM, and EDS, EBSD, and WDS. All these tools are very much useful for characterizing the materials. So today I'm just talking about the cameras. Basically, I want to introduce some of the basic concept of the cameras, which are most important points in the camera, and then I can give you a few examples about application examples, basically. Okay, just this topic we are going to cover. Basically, I just give a brief history of image recording, how they used to do in electron microscopy, and some important parameters of camera in electron microscopy, and how the camera architecture would be there. And then I'll show you few cameras lineup of from the Getan and E-Tech. And then I'll give you some importance of drift corrections in the cameras. And then finally we'll give some application images through these cameras. Okay. So in olden days, it is all these transmission electron images are done through photographic films. And then during 1970s, this CCD was first invented. And in initial days, the CCD cameras were used for astronomy purpose. From the telescopes, when they want to capture some images in the telescope, so they used to use the CCD cameras. And then in 1982, some CCD was directly exposed to 100 kV electrons. Initially, they started using CCDs directly under the electron microscope, but that did not work because of radiation damage from the electron beam. And because the transmission electron microscope, so the accelerating voltage can be ranging from 60 kilo electron volts to almost like 300,000 volts. So then in 1988, the CCD with scintillator and optical coupler was designed. And in 1990, the Getan was the first company to bring a CCD camera into the electron microscopy. So that reduces the need of the photographic film, because the photographic film, taking images on a photographic film, is a very lengthy process. So you need to expose them, and then you need to have a dark room, and then you need to process those films. So when 1990, the Getan made this first commercial CCD camera, so all the images are got digitized. And in 2002, again, there was a direct detection camera was developed with the CCD, but then still it has a lot of issues with the radiation damage. So you need to frequently change the sensors. So that was not commercialized because that's not viable. And then between 2008 and 2009, the commercial CMOS cameras were developed. And now the present trend is the CMOS cameras, because they are fast and then easy to handle. And later, after CMOS camera came up in 2009, probably around 2013, the Getan is the first company to bring the direct detection camera with CMOS, which is the game changer, especially for the biological sciences application, where they need a very low dose electrons, and they want high quality image. So that is possible only with direct detection cameras. And here I will talk about few important parameters of the camera, because many people think about this a lot of basic things about the electron microscope, but they don't pay most of the attention to the CCD cameras or CMOS cameras, because this is the recording device of your image. So the quality and the design has to be perfect to get a better quality images. Okay. So the first and most important thing is the resolution. So basically, when you talk about the resolution, like any kind of a microscope, like you talk about optical microscope or scanning microscope or transmission electron microscope. So people, we talk about the smallest resolved specimen details. So that is what we are looking for as a resolution. But when it comes to camera architecture, the most important thing is the full width of maximum of a point spread function. So this is the most important parameter for any camera design. So I will explain to you about this point spread function, what it is. So basically, when the electron and incoming electron beam falls on a scintillator, where the electron beam is converted into light, and then that light is passes through the fiber optic or a lens, and then it falls on a CCD or a CMOS chip. So that will be converted into digitized image. Now, when this electron beam is falling on the scintillator, there would be a scattering inside that scintillator. So whatever the simple electron, so there would be a small electron smearing will be there on the scintillator. And then further, when the light travels through this fiber optic, so it will have a light scattering. So that makes some photon smearing. So when you see this is the overall smearing, so this is what we call it as a point spread function. So this point spread function has to be properly matched with your CCD pixel sizes. So because it doesn't, if you give too many pixel sizes, like you have too many pixels, like, and then if you doesn't match this point spread function, basically you are doing just a oversampling. So basically it's oversampling, and then basically waste of your memory, and then of course it reduces your dynamic range. So I will explain about this dynamic range in this thing. And then if you put two large pixel, then you might have a very high dynamic range, but then you lose some resolution. So when the camera is properly designed, so they will take this point spread function to the picture, which determines your kind of a resolution. And then the second most important parameter is detective quantum efficiency, which is as a DQE. So basically what DQE in a camera, basically if you give one input image, so the output image, what would be the noise contribution to that image? So in simple way, you can see that, DQE is basically SNR by SNR output divided by SNR input square. So basically that gives a signal to noise ratio. So ideal DQE is equal to 1, but in real world you never get 1. So the closest you can go to 1 would be the best camera, because the noise would be introduced, because as I said, before there would be some smearings in the because of this photon smearing or electron smearing, and then there would be some electronics noise to be added. So all these things comes together, so you never get a DQE of 1, but you should be able to close to 1. So how that will impact your image if the DQE is different? So for example, you give a low contrast picture with some little noise, and then if you have a DQE of 0.33, then it will adding some noise to your output image with a uniform 33% DQE or 0.33 DQE. So if DQE is ideally 1, then you should have in the output the same image without adding any noise. But in real world, so you will have some noise, and then the ideal camera would be close to 1, DQE 1. So this is one important parameter which you need to think about in cameras. And then the next thing would be like sensitivity and linearity. So sensitivity is basically when you are using very low those electron beam. So how you can collect the signal? Basically, that's a minimum detectable signal, when you have one incident electron. So basically, if the gain of the system that output signal is due to single electron is above the noise floor, because you have every system, as I said, before you have a noise floor, which is due to this smearing and electronic noise. So your one single electron producing the number of counts should be above the noise floor. So that will give you the sensitivity. When it comes to linearity, so your basically image quality has to be uniform throughout the incoming electron strength. Suppose when you have a less beam or the more beam, it has to be, image intensity has to be uniform. But in olden days, when you are using the film, that's a linearity, the films doesn't have a properly, they are not linear. So they will go, when the electron dose goes high, then only you can see the image here. So these are the most important parameters. And one more important parameter which we need to think about is the dynamic range. So what is the dynamic range? Basically, the range of values that can be distinguished between the maximum level and minimum level. For example, you take some kind of a gray level image. So you need to, the dynamic range would be that the zero, the complete black, and then complete white. So this would be a dynamic range. So this dynamic range depends on the camera, basically, typically. Suppose if you have like a 14-bit dynamic range camera, so you will get a value between 10 to 16,000. But when you if it is a 12-bit camera, then it is 0 to 4095. So it is very important to have a very high dynamic range, because you want to see the dark level of the image, and then you want to see the bright level of the image in a different gradations. For example, if you see earlier days, probably in olden days, like the monitors, the computer monitors used to have initially they used to have something like 256 colors, and then when the technology progresses, then they have a 16-bit color and then 32-bit color. Now it is like a 16 million colors. So because the color gradient has to be there, that's the dynamic range what we are talking about. So how we can get this dynamic range improved? Basically, to improve the dynamic range, one is to have a larger pixel size, so that it can allow more charge into the pixel of your camera. Or you can use a little bit smaller pixel size, but you can accumulate more number of frames to increase the dynamic range. For example, when you have a 12-bit camera of a dynamic range up to 4095, and then you accumulate 40 frames of that, then effectively you can increase the dynamic range of the camera. So basically, when you want to accumulate this more number of frames, the camera has to be very fast, so it should be able to capture more number of frames in less number of time, like 25 frames per second or like 100 frames per second, like that. So this is one of the important parameters in terms of dynamic range. And then just I want to give you, earlier I talked to you about this CCD and CMOS cameras. So in olden days, we used to have CCD cameras. The CCD camera quality image quality is good, but they are very, very slow. Because when one electron falls on the CCD and then it is converted into photon, so it is exposed as one pixel. To read this one pixel, it has to be shifted using a shift registers to that readout line, and then you need to shift this charge and then finally read out. So each and every pixel has to be read separately. So that's why the CCD cameras are kind of a very slow. Like they used to have something like 1 frame per second or 2 frames per second. Whereas when it comes to a CMOS camera, it is basically the each pixel is read simultaneously, and it's basically in CCD we are measuring the charge, where the charge has to be transferred to the pixels and then read out separately. Where in terms of CMOS we are getting the electrical signal, so that can be read out much faster and then much simultaneously you can do that. So that's why the new technology is now like a CMOS cameras. Now the CCD is no longer used in TEM. Basically, since last 5 to 6 years, the CCDs are stopped. So as I said, the smearing earlier I said about the point spread function and all. So now this is kind of a traditional fiber optic coupled CCD or CMOS camera, so where you will have a scintillator and then light transfer, which is basically fiber optic coupling, and then you have a CCD or CMOS camera, and then that detector will be read out from here. So as I said before, the point spread function, what I'm talking about, so you will have electron beam. So here there would be electron beam smearing, and then you have the light transfer system coupling mechanism, where you will have a photon smearing. So that will limit the resolution of these cameras. But these are cheaper compared to direct detection. These are much cheaper. They can be used for general purpose. Okay, so basically you are converting electrons into light, and then you are transferring this light, and then detect the light into a signal by CCD or CMOS, and then you read it out. So one more problem is that when you are doing this, so this electron beam, when it hits the scintillator, it can produce some backscattered electrons also from this. So that will do further smearing. So then first time the Gatan came up with a direct detection CMOS camera, where we remove this converting the scintillator, we remove this fiber optic transfer, and then we are straight away using electron on a CMOS. Okay, so basically in this case we are converting light to electron to light, and then light to detector, and then detecting the light back to signal. So all these things are avoided. Now directly we measure the strength of these electrons, because these are earlier days we used to have a problem with the radiation damage to the CMOS cameras. So these are specially designed radiation hard and thinned CMOS. So they're typically the thickness of something like a few microns thickness. So with that, because the thickness is so low, the smearing would be very small here, and then there is no backscattered electrons that are adding the noise. So the the resolution of these cameras are very, very high. So one more important parameter you need to think about for any camera. So where you want to install your camera. Basically, if it is your electron microscopy viewing chamber, you can install camera in the side mount or in the bottom mount. So when you see in the side mount cameras, you will have a large field of view, but you will have a very less magnification. Okay, because when you have a large field of view means it is a less magnification. So for example, this Rio 16 can cover this much bigger area, or the bottom. These two are basically the side mount cameras where it can cover large field of view. And when it comes to bottom camera, so you have different cameras, so which can cover the small area, so that will give you very high resolution images. So for materials people where the resolution is very important, always go for a bottom mount camera. And people who wants for life science applications, for them, if the resolution is not important but the field of view is important, large field of view, then they can go for this side mount cameras. Basically, most of the life science applications, they use less magnification and they want a large field of view to cover more area. So these are the important parameters of this camera. And then next thing what we are doing is the drift correction. So basically,
Hello, sir.
yes.
I think we should be finishing this, and if it will be better if you can finish in 2-3 minutes.
Yeah, I'll finish in 2-3 minutes.
Okay, thank you, sir. Thank you.
Yeah. So basically, the drift correction is very important because your sample may not be stable or because of this beam interaction with the sample. So every camera should have the live drift correction, because if you don't have the drift correction, so if the sample is moving when you are taking the picture, then the quality will not be so good. So with the drift correction on, you can see this high quality images. And this is again one more example, for material science, where this is without drift correction, and this is with drift correction. And so to give you a simple line of cameras, what we talk about. So these are the camera lineup. These are like fiber optic coupled CMOS cameras. We have Rio and OneView. Typically, these are for low accelerating voltage, like 100 to 200 kV. And this is high sensitive camera, which can go for 200 to 300 kV camera. And we have a high-end camera lineup where we have a direct detection cameras. So which is alpine camera, which is for 100 to 200 kV for life science application. And then you have a metro camera for 100 to 200 kV for materials. And then K3 is for materials and life science, which is 200 to 300 kV, which is high resolution camera. And so I'll give you quickly a few application examples, and then we can close this. So this is the example of live drift correction. Even though the sample is moving, but still the quality of the image doesn't change. So that's why the live drift correction is very important. So live drift correction can be done if you have more number of frames in the camera. So if the camera can work with more number of frames per second, then it can do the better drift correction. So this is some of the application examples, semiconductor and geolights. And this is kind of a in situ applications where you can do nanobeam diffraction, and then you can collect the data. And then you can do like convergent beam electron diffraction, and then for study for strain in the samples. And this is some of the, like this is a high sensitivity image of a graphene, which is a large field of view. Even if you zoom it, still you will get a better resolution here. And this is some more examples of high resolution lattice images. And this is kind of a one more in situ application. So where you can see you can capture image at a very high frame rate, like 25 frames per second or 200 frames per second, and then you can make a video of that, and then you can do you can record the dynamic changes at a very high resolution. So if you are doing any heating experiments or anything, so this is quite useful. You can record the changes at high resolution. Okay. So these are some life science applications. I'm just giving you, these are a normal, this is like a side mount camera where you have a large field of view at low magnification. And these are some of the life science applications. And these are the applications basically used with a direct detection camera using single particle analysis, where they collect the image of the particle in different orientations. They take hundreds of images, and then they will combine using some software, and then they can make it a three-dimensional image at high resolution. So which is not possible with a normal camera. This is only possible with a direct detection camera. So this is some of the examples, direct detection camera of some life science applications. Just to give an overview. Okay, this is one more. So this is a 2.9 angstrom resolution, which is a very high resolution. This is the smallest protein collected at 200 kb in the world. So that's all for this now. So please let me know if you have any questions.
So any questions related to this presentation, you can ask. So you also know that we already have the stall of this company outside the hall. So you may visit the stall also and can discuss about their products. So sir, thank you so much for giving this information about your products.
Thank you, sir. Thank you for giving us the opportunity to participate in that.
Thank you. So now we start the next session, and for that session, you know that 3 parallel sessions will be conducted, one in this hall and other 2 sessions will be in APJ 4 and 5. So the presenters, they may go their respective rooms, and accordingly the sessions will be conducted. So now for this session, especially in APJ 11, I would request to Professor Vinod Kumar from our department, NSUT Delhi, to chair the session. So I request him to please conduct the session. इसके बाद
सर की प्रेजेंटेशन है अच्छा ओके ठीक So good morning all, and welcome to the session. This session will consist of one invited talk by Professor Mike. Okay. It's fine. Means? It's fine, huh? It's fine. Okay. So welcome to the session, and the session will consist of one invited talk by Professor Sushil Kumar from National Physical Laboratory, and followed by the 5 oral presentations. The invited talk will be of about 25-minute duration, and oral presentation will be from 8 to 10 minutes. And all the presenters are requested to download their presentation before the start of the session. So I would like to request all the presenters are here. All presenters, Dr. Bhunesh is here. Dr. Swapnil, yeah, you have uploaded the presentation? Okay, fine. Dr. Komal, you have uploaded or give in pen drive? Just yeah. Dr. Mohammad Asif, yeah, you bring up. Dr. Karan Grover. So all please bring their soft copy of the presentation at earliest. Yeah. तो upload. कहाँ पे? अच्छा, okay, fine. Just a minute.
Recording stopped.
टाइम लगेगा सर उसमें, वो जिप होएगी फिर अनजिप करना पड़ेगा।
पेन ड्राइव से ही ले लेंगे हम। हाँ 11 में चलेगा और यहाँ जा कर के रिकॉर्डिंग शुरू कर दीजिए।
पीपीटी तो अपलोड करेंगे।
इसको बंद कर दीजिए। अच्छा बंद, ये कौन सा वाला रिकॉर्डिंग चल रहा है? अच्छा वो मेन वाला चल रहा होता है।
तो इसके यहाँ की नई बना लेते हैं
और इसको कन्वर्ट करते रहते हैं। ये हमारा
Recording in progress.
ठीक है। और शेयर स्क्रीन का कर दिया होगा? ठीक है।
एक वो बना लो फोल्डर।
और माउस यूज़ कर लीजिए जल्दी से। डे 2 डाल दीजिए इसमें।
सेशन के नाम पे डाल दो सर, सेशन 4।
अच्छा ठीक है।
इजी रहेगा।
इसको ओपन भी कर लीजिए और वो वाला बंद कर दीजिए। शेयर करना पड़ेगा।
नहीं शेयर कर दूँगी, मैं चेक कर लिया इनका। ठीक है, ये इनवाइटेड वाला इनकी निकाल दो। ये इनकी दे दो। कौन आ गया? कोमल भारद्वाज के नाम से। ये बता दिया नाम। कौन सी वाली है? थीसिस नहीं, प्रेजेंटेशन नहीं होगा ना।
ये क्या है मैम?
ये कुछ भी हो सकता है, तो इस पेन ड्राइव तो खाली लेके आया करो। नहीं इसमें आप इसमें चाहिए नीचे। इसमें नहीं नीचे इसको स्क्रॉल करेंगे ना तो
नहीं
इसको स्क्रॉल करेंगे।
अरे कितना सारा लेके रखे हैं।
और नीचे सेशन आपको नोटिस स्टार्ट होने से पहले आपको अपलोड कराने थे। आपने अपलोड की थी मेल पे? हाँ लेकिन है ना उसमें।
मेल छोड़िए।
चलो ठीक है, आप बताओ।
एक दीजिए।
पहले वाली किसकी थी?
यहाँ पे तो भी तो आ रहा होगा आपका।
हाँ यहाँ पे
ये
पीपीटी
बताइए कौन से फोल्डर में है?
नहीं फोल्डर नहीं ओपन ही है। या इसको डेट मॉडिफाइड करेंगे ना तो आ जाएगा।
टाइप हो गया, पीपीटी सारी यहाँ पे। ये तो पीडीएफ है, ये सारी पीपीटी है। कौन सा है?
ये डेट मॉडिफाइड पे क्लिक करेंगे ना। हाँ ये सबसे
कोमल
ऊपर
भारद्वाज। सेशन वाला कहाँ पे है मैम आपका? इसमें नहीं है, डाउनलोड में। डाउनलोड में
APG 11
APG 11 सेशन 4। ठीक ठीक है, अभी इनका चलाना है ना।
अभी इनकी निकाल दो सर, थोड़ी ले लूँ मैं। पहले वाली कौन है?
लंच वालों, लंच के बाद वालों का बोल देना लंच में दे दें सब लोग। हो गया।
इनकी ये करण ग्रोवर की है अभी।
किसका शुरू करना है?
इनकी ऑन करण ग्रोवर।
नहीं, छोड़ दो। यहाँ से ऑन करो। नहीं नहीं, एक मिनट, यहाँ से ये अनम्यूट और वीडियो ऑन, और एक मिनट इसका माइक चेक कर लो। ये वाला, हाँ सही है, ठीक है।
So, good morning again all, and welcome. Just a minute. So, hello. So, welcome to the first lecture of this session by Professor Sushil Kumar from the CSR National Physical Laboratory, New Delhi. The title of presentation will be Advances and Challenges in Solar Photovoltaic Technologies. So, before the lecture, let me introduce Professor Sushil Kumar. Professor Sushil Kumar is the Chief Scientist at CSR National Physical Laboratory and also an honorary professor of Physical Sciences at the Academy of Scientific and Innovation Research, ACSIR. He obtained his PhD from IIT BHU in 1997 and joined NPL as Research Associate. He was a Boycast Fellow at the École Polytechnique, Palacia, France during 2002 to 2003. He has significantly contributed in the area of solar cells, plasma-produced thin film materials, and coatings. Presently, he is heading the photovoltaic metrology section of CSR NPL towards the development of primary and secondary standards of solar cells, development of waste management technologies such as recycling of waste solar modules, plastic waste, and other electronic waste for their societal applications. Silicon-based heterojunction solar cells covering basic and applied research spanning from wafer-based silicon photovoltaic technology, thin film, to the latest concepts such as organic and perovskites or organic/inorganic heterostructures-based solar cells. He has over 100 publications and 10 patents. He is an expert member of various national committees, including funding bodies, and is a governing council member of National Institute of Solar Energy, NISC. So welcome, sir, for the lecture. Yeah.
Thank you, Session Chairman, Dr. Vinod. For giving my nice introduction. And also I would like to thank organizers and particularly my dear friend and my senior as well, when he was in the NPL, Dr. Sukhbir Singh ji. So thank you very much. And Madam Ranchna, you also thank you very much. It's my pleasure. Yes, this topic is in my heart, basically the solar cell. As such, initially I started working on thin films, various aspects, hard coating, diamond-like coating, optical waveguides, many applications, but finally I landed to this solar cell. And when the Jawaharlal Solar Mission started in 2010, so again we re-energized ourselves in the NPL to contribute more towards this national program. So I will highlight some work, what we are doing and what presently the challenges and advances are there. Though photovoltaic has advanced a lot, you know that is a, we can say, mature technology, particularly for silicon solar cell. And in the solar mission program, government has launched big programs installing solar parks and other things. If you see this slide, the India is moving ahead with other countries in the renewable energy expansion program, and India is committed for net zero. In the morning also, Professor Misra was mentioning the maintaining 1.5 degree Celsius temperature, the global warming is a concern for all of us. And India is also committed to that, and because of that, this national mission program was launched. And if you see the data, this 2030, 280 gigawatt is a huge. And presently we have more than 65 gigawatt already installed by March 23. And the total capacity of our power production is about 416 gigawatt. These are the magnitude I am giving just to see the solar PV where it is now. And still we have a challenges there. And at the bottom, the one data I have shown, 1.3 gigawatt. It's a very interesting. When we got the independence in 1947, the total capacity of our country, electricity production, was just mere 1.3 gigawatt. And now we have, in the renewable itself, more than 65 gigawatt. This photovoltaic, we have more than 65. You might be knowing that ISA, that is basically it is an international alliance, and India is a founder member with, along with the France. And this is basically the alliance, the countries which are between the Tropic of Cancer and the Tropic of Capricorn, those countries which are blessed with the sun, so that they can utilize maximum the sun power to have the electricity for sustainable development. Solar power, the photovoltaic panels are installed for producing electricity. And in my presentation, I will highlight it is not so green. Basically, you will have the waste after its end of life. And that is a big challenge for all of us. And we have to address. This one photograph is given, it is in the Jodhpur district, that is called the Badla Solar Park. And it is a capacity of more than 2.2 gigawatt. Now these are the some solar park given here, and you see that histogram, the chart there. So India is in the fourth in the global ranking in terms of installation. It is little older, about the 60 gigawatt it is given, but now it is precisely 66.5 just in the April month. The data is with the MNRE. And the global capacity is more than 1,000 gigawatt is already there, and by 2050 we'll have 5,000 gigawatt or so. So with this, you know that the photovoltaic, the solar cell, essentially a semiconductor device. You need a material, and the technology depends upon the material, which kind of a material you are going to choose. The choice of a material for solar cell is important. And in terms of this, our choice, the well-proven material is a silicon. And silicon photovoltaic and the panels produced there, and the 95% of the market or the installed coverage is of the silicon solar cell, whether it is in a multicrystalline form or the monocrystalline form. And rest 5% is a thin film that consists of your gallium-based solar cell, gallium arsenide essentially, and mainly it is used for the space application. It has basically it's a very costly development process. That is why it is not that popular for terrestrial application. The amorphous silicon CDT, cadmium telluride, and CIGS, that is copper indium gallium sulfide, is a well-established technology in the thin film. and having a 5% market. But amorphous silicon is also not doing well because of its limitation. CDT is somewhat is progressing well in the thin film category. Others are emerging technology. They are at the laboratory scale. And then in the research lab, about as for the data says, about 99% people, the laboratory researchers, they work on these emerging photovoltaics. There are two reasons. One is, yes, it is emerging. Lot of science needs to be done. Lot of understanding has to be done. That motivates researchers to go into this field. And apart from that, these processes are cost-effective process. A simple lab, you don't need big infrastructure. You can easily make these solar cells. So that is the reason, but still this technology, the emerging technology, has to establish for commercialization. This is a chart. Basically, those who are in the solar cell community, they know that the NREL, it is in the laboratory in US, they keep the data of records. You know that in the Olympics, the athletes or the sports person make a record, and there are agencies which keep the record. In the same way, the efficiency of solar cells are also measured by NREL, and each year they publish their data with the newer efficiency. And here you can see the variety of material and the silicon. Because I'm going to focus more on silicon solar cell because the established technology, but still lot of challenges because country wants that, because silicon and all the installations in the country is going for the silicon solar cells. You know that the solar cell, the smallest constituent part of a module basically in the module you have a number of cells there, whether it is connected in series or in parallel configuration, depending on what amount of configuration you want, the current and the voltage, so that you can have a required power for your use. So there is always a difference between your cell and the module, and this is the curve it is given for some of the cells. Though perovskite it is indicated, but it's not commercialized in the lab scale only, but it has some futures definitely because of its cost effectiveness. This is a very interesting curve, and on the basis of that we can see the history of the solar cell. पॉइंटर होगा क्या आगे है क्या नहीं हाँ नहीं इस पर सॉरी आई अंडरस्टैंड हाँ मैं यहाँ से मैनेज करूँगा राइट हाँ इट्स क्लियर डिजिटल डिस्प्ले फाइन हाँ तो हाँ इफ़ यू सी in the silicon solar cell, essentially it is a p-n junction. You have a p-type, n-type, wafer is taken, diffusion are going there. So I can just quickly, I go to this basically, then I will come back. In the p-n junction solar cell, basically these are the p-n junction solar cell, and in the thin film or in the emerging technology, you can have a PIN and other things. It's a diffusion based, or you can have a drift based assisted conductions. So in the p-n junction, if you have a p-type substrate, so you should have a n junction also, a n-type. And that because of the with the diffusion process, these junctions are formed. And what I want to say you, initially when the solar cells were made in a simple configuration, just you have a p-n junction and then the contacts you have. And these are the cells of lower efficiency, 12 to 14% or so. With the black triangle it is shown here. It is without passivated. What passivated means, the passivation is a process. You know that the surface states are there, and you have to make the unpassivation of that. Dangling bonds are there. So by some kind of a coating, it is possible to do that. And later understanding developed in 80s or so with this blue down triangle, you can see. Then passivated emitter kind of a cells came into the existence, and efficiency got improved and touches up to 20%. So about, if you see in a span of around 20 years or so, the researchers were struggling with the efficiency. So in those days, only efficiencies were maximum over 15 to 16% were there, and commercialized cells were hardly with the 10% or so. So after this 80s, the research particularly done in Australia, by Martin, Professor Martin, this kind of a structures came and you have the efficiency more. And in the 90s, PERC, another kind of a solar cell. I will give you details of this also, how the designs, and still challenges are there in that. And this, your arrow curve, if you see, these are the basically for the module, the commercialized one. The aluminum BSF, basically this is the back surface with the 24% and 20% and 24% in the PERC, and 25.5% is also just recently in the commercial setup it is shown, but somehow it is not that commercialized. It is shown in the big industrial line, but it is expected it will definitely cross in 25% in the industrial line as well. And these are the technology forecast, how basically with the time. We know that the silicon solar cell are there, but there also a lot of technological improvements are taking place, and because of that this cost is reducing and your efficiency is improving. Basically that is what the need is, that is what we want. And you know that in India, when this module installations are there, the installers, basically it is these things come with our Solar Energy Corporation of India. It is the MNRE autonomous body. So they take care of all the installations in the country, and they go with the reverse bidding. And we achieved up to 1.9 rupees, just 1.9 rupees per unit. You can imagine, you are getting electricity bill of your thing. Even in the Delhi we have subsidies. So 1.9 production unit is very less. So it is quite comparable or even lower than the grid parity and electricity produced by other means like your thermal power. So it is very interesting that now it is quite competitive. And these are the technology mentioned from 21 to 32. And if you see now we have a 23. So mostly it is a PERC based solar cell, and in the future tandem solar cell and other thing will be coming. Now, what limits the efficiency of solar cell? As a semiconductor material and the material scientist, we know that if any material is there, you should have a absorption of light there. And what's depend? It is the band gap of that. And band gap decide, yes, how much absorption is there. And this is theoretical limit, and it is shown that maximum you can have it 33% of the efficiency by any known material, a single element material I mean to say. You can have a heterojunction or the tandem junction solar cell, beyond this efficiency can be made. And for the silicon it is given 29.4%. And what it is achieved? It is achieved 26.7% already in the lab. So now we are very close to theoretical limit, and that is why this is a challenge for silicon solar cell. We should have some way to enhance the efficiency of solar cell about 30% or so. So already it is crossed beyond 30%. I will show you some data. So lot of development taken place, and this is just for the students. This slide is only for the students. Basically, you know that ultimately what limits this efficiency? Your absorption is there. As I mentioned, 90% of the theoretical limit is already achieved. It means we have developed a lot of the things, quality of the material, but still some losses are there, and those losses can be of this. Here it is given for the 5 things. The lattice thermalization, you all know, when your photon energy is more than the band gap, your lattice get vibrate, and that loss as a heat. You can have a junction voltage loss. Basically, when you have a junction formation, there also your loss can be formed, and the contact, if your contact is not proper, or the recombination losses, or at all your photon is not getting absorbed, just it is passing through the material. This figure already I have shown you, and what other thing I want to emphasize you, simply it is a p-n junction, but in a design it is shown as a n plus p plus. What does it mean? It means when you have a wafer P, and when you are doing the diffusion heavily n-type, like for the p-type, normally we take POCl3. So we have a layer of POCl3, and we put our wafer into the furnace so that your diffusion can take place, and it is highly n-doped. And at the back side also again we do the diffusion of P type, P plus normally the aluminum. So this way your structure become N plus P plus. And this is a conventional design, and this technology was there for almost 25 years in the market. Even still some industries are producing it, but its market share as on date, it is only 10 to 15%. Other technologies are coming up now and already in the market, that is per solar cell, I will give you. So why after all it all needed? This is for the losses. If you see that your pie chart, so 49% of the loss is from the back contact. So majority of research was taken place in the recent past on the back contacts, how you can improve the back contacts, how you can minimize the losses. That was the main aim. Just going for that losses, I want to give you a way how these solar cells are made so that we can understand what the improvement we are going to do in this solar cell. You know that when you take the wafer, you have a texturing, then you have a diffusion, then anti-reflection coating, then your screen coated back and the front contact. So this is what the BSF is there, and you can have a IV characteristic and the power. Now, what improvement was taken place? This is a very latest technology, but industries are using it. That is basically, as I mentioned, the back contact. In the back contact, it is not a completely contact. Basically, you have a dielectric in between layer. If you see here, these are the grooves are made, this green color at the back contact, and this is done by the laser grooving or by some other